when you open your SPSS, you will see the first login thing. Okay, so we're going to discuss about data view, variable view, and importing all the data on your SPSS. So you will become familiar. All you need to become is to become familiar with and know how to navigate between the different windows in SPS. This is a computer application, so you're applying it into your research. Know how to write a data file, and you have to know how to import data from Excel to the SPSS. So the SPSS is short terminology, and acronym terminology for statistical package for the social sciences. The different windows of the SPSS are the output, syntax, data view, and variable view. So the SPSS will show the command that have been executed and the corresponding results and outputs of those commands, where you will find tables and graphs that you produce as an output. So the output, this is a different window. It will appear suddenly if you click save on the SPSS, an output window will suddenly appear, an extra output window. So be careful with the windows that you choose, whether it's an output or the variables that you're looking for. This output can be saved in SPV file, or it can be opened using SPSS also, or exported as PowerPoint. It can be exported as XLS. It can be exported as document. It can be exported as a PDF. So the output, you can be saved as an output, but if you export it, you can no longer reuse it. You have to do another output in order for you to re-export it again. So the syntax file is the easiest way to keep track of everything you do, and it enables you to go back and either re-examine your analysis or run the same analysis again. So when you put on save as, and you open your file and you put here new and you put here the output, then it enables you to re-examine your analysis and run it again. So the SPSS allows for automatic passing of every single procedure you run, or alternatively, you can type in procedures yourself. So this is an SPSS, and then you can put in the procedures that you wanted to use for your analysis. It also makes it easier to run the same procedure on different data sets and to run the same procedure multiple times. So there is a multiple time procedure that you can use to run the SPSS over and over again. So you run syntax by clicking the green arrow. There's a green arrow there, and the button that you always want to run part of your syntax, and highlight that part and click the green arrow. Or it can be saved as SPS file and can be opened by any simple text editor like the Notepad. Okay, so the color coding, such as the dark blue, the green, the red, orange, green, gray, and black, they are just codes. The dark blue are the procedures, and the green are subroutines connected with the procedure, and the red, orange are keywords indicating choices you have made, and the gray comments the line that must begin with asterisks, and the black are the variable names. So those are the color codes of the SPSS. As you can see, there's a green, there's a yellow, there's a black, okay, there's gray. So the columns are variables. These are the variables, whether there are demographic variables. This is demographic variable. Age, gender, marital, child, education. These are demographic variables, but they are also called variables. So you have known the variables already: confounding variables, control variables, mediating and moderating variables. Those are the variables that you have. And one of those variables that is showing now are the demographic variables. They might be a mediating variable, okay? So the rows are the cases. The number of patients are in the rows, because the rows are the ones that shows you how many respondents that is inside your SPSS. And this is the variable view. So there's a difference here. As you can see, there's a very small icon there. It says whether it is data view or variable view. So the data view is the one without the circle, and the variable view is the one with the variable. So the variable view has a different columns, different rows. And the rows of the variable view are the number of the respondents, and on top of it are the names, the types, the width, the decimal, the label, and the values and the columns. So I will show you. I'll demonstrate to you how to use the SPSS today, with regards from the very beginning of your Google survey form until you export it into your SPSS. So the rows are the variables here on the on the variable view. You're clicking the variable view now. The rows are variables and the columns are the variable details. So there is a numeric, there's a string detail on that column, and we will change it into numeric because you are supposed to analyze it based on numerical codes. And there are labels that you need to put there, and there are values on each labels that you have decided to put. So the nominal this is the variable code on the far end of your SPSS. These are the variable code that sets numbers, but where the numbers in themselves mean anything else. So such as the gender, 1 is to male, 2 is to female. You can alternate this. It can be the value nominal 1 is female and the value nominal 2 is male. Those are two options only, so you can alternate it. Even yes or no, there are also two options. You can either alternate it. Yes is to 1, no is to 0. Oh, yes is to 1, no is to 2. Or 2 is to yes and yes, no is to 1. The ordinal are the order of, that means you cannot go from 1 to 5 and 5 goes to 1 and 1 goes to 5. So there's an order. A variable where data is coded as numbers, like with nominal, but where the codes can be arranged in a meaningful order. How much do you agree with this statement, such as the highest achieved level or the lowest? So there is an order of strongly, not agree, neutral, agree, and disagree. Those are the ordinal. And the scale numbers are the number itself, okay? Where there is a number, for example, the age, that's a scale, because the age is not an order of, there's no such thing as the order of this, but the scale. Okay, where the number itself is a data, like blood pressure, you can put there, or temperature, or tax, or revenues, or the spin magnitude of an electron. Oh, those are the scales already. Or electron configuration, 1s1, 2s2, 2p1, 2p2. So those are the scales already. You have already the scales. The number itself that you put there as the variable, the data variable that you input, the number itself. So the name variable are the names, starts with A to Z. So there's a alphabet there. And the types of numeric string data, number, words, dates, etc. are the types. And the width is how many characters will be available in the column itself, because you can expand the width. You know, if you have a lot of numbers, if you don't expand the width, then they will round it off to the nearest tens. That means if you reach 5, they will round it off to that 5. If your column is just as few as, if the width is as few as 7 or 8 or 9. And the decimals is how many decimals do you need? Because sometimes we only need 2 decimal places, so they will round off the third. If it is less than 5, then it becomes infinitely 0 at the end. It will just round off to the decimal that you have chosen. How many decimal places do you want it to capture once you key in all the variables? And the value, the label, are longer description of the variables. That means the label can be a lot of sentences and a lot of phrases. Values for nominal ordinal, this is where you code your variable. That means you have to decide what the code of the variable is. And the missing, if you want to give missing data in a different code, then there is another code for that, missing data. The columns are the columns. The columns are how wide you want the column to be. And a line is a line to the left, a line to the right, or a center alignment. The measure is where you choose scale or nominal or ordinal. So the last part, on the last part of the SPSS, there are measures, and they can put there, it's either nominal, ordinal, or numeric. So we will choose or nominal, ordinal, or scale. So we will choose this measure. The role gives the predefined where you want to start or how you want to do the starting roles. So especially when you have several files or data sets open at the same time, it is important to know which spreadsheet is the active one. And this is the one that you will be using the analysis you do. The SPSS indicates which is the active window with a small cross variable there on the top. So that's the active window. That's the one that you're using now. If you open a lot of SPSS, there's tendency that you can open a lot of SPSS. And these are the icons. So there's a lot of complexities on the SPSS icons, such as open file. These are the icons that are necessary for you to remember. Open file, save file, print. You can print the SPSS though. Most recent procedure, undo, redo. If you made a mistake, make it undo. You don't type it again. Just undo, 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 and then it will go back, revert to the previous thing that you have done. You might make a mistake and click something different, so you just have to undo. And if you think that you need to redo, just click the redo. Go to cases, that means it goes back to the cases. And go to variable, that means it goes back to the variable. Variable information, descriptive statistics, these are so important icons that you need to remember. The descriptive statistics, the find and search, if you're searching for names, if you're searching for the genders, you can find and search. Insert cases, you can also insert cases. Insert variables, and split file, you can split file. Icon description of weight cases, select cases, choose if data or label is shown, and use the subset, and then use variables, and then check spelling error. Maybe you have a spelling error there. You can check as well your spellings. So all you have to do is open the data file, and I have shown you last time how to open the data file using the Microsoft Excel that you have downloaded from your Google survey form. That's an Excel. And choose paste and not open. If you want to paste something, you can paste so. But if you open something, you can also do open. Just make sure you select the Excel if you want to open the Excel. And file import data or text data, you can also paste the text data there, and dialog box will open, such as TXT, DAT, and CSV or tab files. So text import window, you can also import the windows, when you have an Excel that you want to copy and then import it on the SPSS, you can also do like that. So there's our text import wizard. Each line represents a case, and all of the cases, you have to click there how many lines and how many cases do you have. So you can put there text import wizards, such as the limited wizards in semicolon. You have to click the semicolon, and then it separates what are the thing that is not there or that is supposed to be there, or some separations of the demographic variables, such as gender, age, marital, child, education, and other demographic variables that are available there. So the next one is the variable name. You have to put the variable names because it's so difficult without the variable names. And I will show you how to make the variable names. It has to be a syntax or a variable that you will remember most of the time. And these are the file import data and the CSV. We're going to show you how to do the file import data and the CSV, because sometimes the CSV requires only the variable view that will import it to an Excel. And the read Excel file can also be placed there so that you can read the Excel that comes inside. Okay, so when you have very large data set, it can be useful to split the screen so that you have 4 panels all showing different sections of the spreadsheet. All right, and delete or insert case variables when you are in data view. So when you are in data view, you can delete or insert case variables inside the SPSS. So let us see how the SPSS works. All right.
Hello everyone, we're gonna go for the online survey form and transfer it to the SPSS software from the online survey questionnaire into the SPSS software. This is your Google survey form from the online, and we're going to transfer it to the SPSS, but we're going to go for the responses first. This is the icon responses, and we're going to click that icon, and we're going to we're gonna get your um, your Excel, Microsoft Excel from this view in sheets. And we're gonna click this icon, view in sheets, and then we're gonna click download responses. All right, so it's here already from the download icon. You can find it here. Sometimes it's here, sometimes it's here, but as for my device, it's found here on this icon. And I'm gonna go for my downloads folder. We are now here at my downloads folder, and we have already opened the Microsoft Excel from the downloads folder. All I want to do is remove this timestamp and username. I'm gonna delete, and also this the consent. I'm gonna delete that consent, and the phone number. I'm gonna delete that as well. I do not need those. So I'm gonna open this here and uh, try to see my variable. So if you want to get the two languages all together in one, you have to click the view in sheets. This view in sheets is found here in this icon and not this icon, because the icon just now just didn't give us the two languages. So if we click the view in sheets, will be transferred to the view in sheets in the online Microsoft Excel. We have to click the file because we need to download. Okay, we have to download it into Microsoft Excel. So now it's becoming downloaded here. Instead of giving us the zip file, it gives us another sheet called the Microsoft Excel, and no longer the zip file, because the zip file cannot include the two languages. And I'm gonna go back to my download folders to open the Microsoft Excel that I've already downloaded online from the Google survey form, online forms. So now I have seen two languages here already available. I'm gonna remove the timestamp and the email, delete that. I will gonna have to delete also the consent form. I don't need a consent form, and I also don't need the phone numbers. Delete the phone numbers. I need the age and the other variables. Now I can transfer all these into my Microsoft Excel. From the Microsoft Excel into my SPSS software. And I'm opening now my SPSS software. I'm gonna go to the files. This is the file icon. Click this file icon on top here. All right. And then open data. So I'm opening my data. Okay, and I'm gonna go to my downloads option. This is the downloads icon, and I'm gonna click, I'm gonna change this SPSS into Excel. But I have to remember that I need to close my Excel before I can open it from, I transfer it from Excel to SPSS. I have to close the Excel first. So let's click the file, open, and then data, right? And then go to your Excel and go to your downloads folder and click the Excel that you wanted to open in the SPSS. So remember to click the Excel here on the icon Excel. And since this is the one that we wanted to transfer to the SPSS, that's one to need to open, click open and click OK. All right. And we're going to go to your IBM again, since we have already transferred all these from the data view. This is the data view. We're looking at the data view. Okay, we're going to go to the variable view later and we'll fix that. Okay, so these are the data views, and all these respondents are here. And we can see that we have 168 respondents. And since this is an example, I'm gonna remove this. I'm gonna clear. And if we look at the data view, it's 167. So 167, removing the example from the one that is shown above. 167 is the total respondents. And we're gonna have to change all these string variables into numerical. We're gonna go to the folder, the variable view, and click this icon called variable view. Okay, this is the variable view, and as you can see, it's not the same with the others. So we have to copy and paste everything that we've seen here from the Google Online Survey form. All right, we are now looking at two windows. One is the SPSS, and the other one is the Google Online Survey form. So we're going to transfer the variables from what we have on the online into the Google survey to the Google survey form into the SPSS versus the group. Okay, this is the demography group. Mm, we're gonna have to change this into demography one. Demography one. That's called the demography one because here it says social demographic, social demography. This is one of the variables. So the control and the experimental are one of the demographies that we will change. And all we have to do is copy this, double click, copy, and paste here. And double click this, copy, and then put here one, paste, control, double click, copy, put here two, paste, experimental, and then click OK. Next is the age. So the demography 2 will be the age. Demography 2 will be the age. All you have to do is copy this, copy, and then paste. And whatever is found here is whatever you put here on your icon. It's very hard to have a bilingual survey questionnaire since you need to copy and paste it from the main original source. It has to be the same exactly, especially if it is from string words and you want to convert it into numerical. It has to be exactly the same as the original document from the Excel sheet that you have transferred into the SPSS. So remember, uh, to not put some space after this icon has been copied and pasted on the SPSS value labels. This is the value labels. We're going to go to the value labels because we're going to put the values here in a numerical format so that it can be converted from numerical to string, string to numerical, string words to numerical words. And then I'm going to click the add and then click the OK after I'm finished with all of these. So just now I highlighted all of these because it will go out um, on your main SPSS data view. And if there's a space, just remove the space, make sure there's no space, and then click add. Number 2, paste, and make sure there's no space on 31 to 40. Okay, copy this and cut, then add. Number 3, paste. There's a space here. As you can see, there's a space on the front of 41. So there should be no space there. Be mindful of it. And then cut. Make sure no space here after the 50. And then number 4, will be the last variable, the last label. 21 to 16, no space in between, no space on the front, no space after the number. Then click add. Then click OK. This is the OK button. Okay, so the age is there. Next is the gender, demography number 2, gender. Highlight this, copy, and paste here, and then this will change to demography 3. And demography 4, uh, demography 4 will be the body mass index. Copy, then paste it here. And the finally is the marital status. Copy, and then paste here, and then demography 5. So there are 5 demographies that you have. It is a very religious practice to copy from the original source rather than copy from the SPSS that you're looking at here, because you really cannot rely on those transferred um, messages. So you have to be very religious on copying from the original source. So the gender is male, copy here, and then get to the values and put the values of the gender, the body mass index, and the marital status. Click here, anything will do. Male can be 1 or female can be 1, as long as there's no space in between, and click add. The next is the female, copy number 2, female, then add, and then click OK. It's either of the two. 1 can be female, 2 can be male. Either 1 or 2, it's up to you, as long as exactly the same message or the same values are found from the original source into your SPSS, because that's what will be reflected on your data view found here below data view. This is the data view from your SPSS. As long as it's exactly the same, that's what the data view will show. Body mass index, you have to copy all these. Copy, this is the first value, and then click label paste, and then click add. Okay, exactly the same. Copy the number 2, and then paste it here, and then click add. And then number 3, copy value number 3, here, and click OK. And finally, the marital status. Single, this is the value, 1. Either single can be 5 or married can be 1. It's up to you, as long as you know what you have done. Paste, married, divorce. I'm making it in the chronological order because later I'll show you why I wanted it in chronological order, so it doesn't confuse me when I go to the original source of the Google Online Survey form values into the SPSS. I want it in chronological order like this, so it doesn't confuse me. So it's in a chronological order. No prejudice for chronological order. Just put here 1, 2, 3, 4, 1, 2, 3, 4 in the order of. Okay, so now we're finished with the demographies, the 5 demographies. And if we go to the SPSS, further here, we can see the measures. And if we look at the measures, what do we interpret of the nominal? The nominal are more of the number, so they are all nominals. The order around the order of which one is number 1, which one is number 2. So here, nominal can be either 1 can be male or 1 can be female. That's what you call the nominal. And if you're gonna change this to ordinal, you have to just click from here. Okay, the measures can be ordinal or nominal, but For this, it's only nominal. Okay. And the next is the outcome variable or the effect variable called the main survey. All right. In research, we call this the outcome variable or the effect variable. Or here on the main survey is called diet as a lifestyle outcome variable number one or effect variable number one. So we're gonna put here in the code of the name as outcome variable called diet underscore lifestyle. That's the effect variable number one or the outcome variable number one. And we're gonna put the label here, what the label is. So copy and then paste here exactly the same as what the label is found. And for our values, all we have to do is copy the values found here on the original source, which is strongly agree, agree, disagree, and strongly agree. This is what we call the ordinal scale of measure. You cannot put one is the disagree and two is agree and three is strongly disagree and four is strongly disagree. It has to be in the order of, you have to make it organized in the order of. And that is how you interpret nominal and or the ordinal. So I have to copy exactly from the original source into my SPSS. So we're gonna go for number one, strongly agree. I do not want space. Just now you saw a space. I click backspace so that it doesn't show any space here. Next is the agree. It has to be number two, agree. Paste. See, as you can see, there's a space found on the blinking icon cursor. Means we have to click backspace. We cannot afford to have spacing. The disagree, and that's number three. And then click add. Since there's no space here, I don't need to make backspace. Add, and then go here. Number four, and then click add. So it's either you decide whether the strongly disagree is number one, two, three, four, as long as it's in the order of, it has to be in the order of. I want to follow the order accordingly. So when I go to my variable view, to the data view, and I transfer the string words into a numeric, I will not be confused because I have the pattern of following it chronologically from the original source going down to the SPSS. So number one, two, three, four is chronological based on the original source. One, two, three, and four. The other one is four. The fourth one is the four. Click OK, and all you have to do is copy this and paste it here on the other side of on down here on the next outcome variable, which is also a diet. A diet has about one, two, three, four, five, six main surveys for your label on diet lifestyle. Copy this icon, this name, code name, diet lifestyle. This code name, diet lifestyle, and then we're gonna put it here on the next, which is called the next um, survey question, number two. And the number two is reducing sodium intake from the original source. Copy the original source and paste it here exactly the same. And they're still both having the same value, so it's still the same. And just continue going on until you get into the sixth outcome variable called diet lifestyle. And then number three, um, the number three from the original sources, I regularly consider foods. So copy the original source from the online survey and paste it here and copy this again and then put it. If you're gonna copy and highlight, just simple highlight and then paste it, it will not be pasted because it will say that this variable name is a duplicate. This variable name duplicates an existing variable name, and therefore it's an illegal character. So all you have to do is go inside the box and make sure that the cursor will appear, and then highlight the blue highlight icon before you paste it. Then that's the time you can change the number from 3 to become 4. So the fourth survey from the outcome variable diet lifestyle. 4 is avoid processed food. Okay, based here from the original source. And then next is number 5, diet lifestyle. Paste here, number 5. Um, the number 5 is the original source says my diet is tailored to support health. So I have to copy and paste it here. And then uh, diet lifestyle will be number 6. Paste, and then number 6. And then copy, and then paste it here. Paste. All right. So we have 1, 2, 3, 4, 5, 6. Diet lifestyle 1, 2, 3, 4, 5, 6. These are the outcome variable called diet as a lifestyle. That's the effect variable. And all we have to do is copy the values because we haven't copied the values yet. All right. Copy the values and highlight and then paste here. That's all you have to do. Highlight and paste. And that's your effect variable number, a diet lifestyle called the diet lifestyle. Another effect variable is emotions as lifestyle. So all we have to do is copy this and paste. We cannot just put here emotion space lifestyle. It has to have underscore on this name uh section, or the code names. We cannot have spaces. It will be an illegal character if you put space. So this is the emotional lifestyle number 1 from the original source. We're going to copy it again. Copy and then paste. Original source, emotional lifestyle, outcome variable, effect variable. We're going to emotional lifestyle number 2. That's the next. From the original source, we're going to copy and then paste here, and then copy this, and then paste here. It's very religious to do it on this way so that it doesn't confuse you whether how many effect variable you have already done, because you will have to alert yourself that you have not yet reached the fourth effect variable. And if you have a lot of effect variables, it will be so confusing if you copy and paste without religiously checking whether you're in the right track. We are so lucky that these effect variables are not so much. Copy emotions, paste. Number 6. So there are 6 survey questions for the code name emotion lifestyle as the effect variable emotion lifestyle. So we have completed all the 6 outcome or dependent or effect variable called emotion as a lifestyle. We coded it. The code name is emotion lifestyle 1 to 6. All I have to do is copy the values because it's the same value as the above. It's still strongly agree, agree, and disagree. And that is how it is recommended for you to do online survey questionnaire, having all of it, all the values to be the same. And all I have to do is highlight all the values and paste it. And now, voila, it's there. I just magically pasted it. And we're gonna go for the next outcome variable called career pressure, career as a lifestyle, career underscore lifestyle 1. And we're gonna go to the original source, copy the original source and paste it here. Next is career lifestyle. I could just do career lifestyle one by one if it's not so much for you uh, to remember. Yes, you can do something like that, but it's very religious to do it one by one. If there's so many outcome variables having the same code names, if this code name is about 25, 1, 2, 3, 4, 5, 6, you have to start with 0 because there are two digits already: 0, 1, 0, 2, 0, 3, 0, 4, 11, 12, 13, 14, up to 25 code names and the same outcome and the same code name for the same outcome, and having the survey with different surveys. Be religious when doing it. Put it one by one, two, and then go to the original source of the survey questionnaire, copy, and then paste. And then next, type down the number two outcome variable and go back to the original source. It's nice to be religiously doing it, but if you can memorize it, like only six outcome variables, then you may as well do it like this. So the values will be copied again and then paste. Remember to be religious with the values because some of the values may change. Maybe this value is strongly agreed, disagree, and some of the values may be um, yes and no, Likert scaling, and that will be confusing for you already if you have 25 code names for the same outcome variable of your survey questionnaire. Therefore, the values having different being uh, scaled or having a different Likert scale, it will be confusing for you. The next outcome variable is a unique one of a kind way of life. So let's put it as way of life. Way of life can be coded as way of life. Okay. So let's paste it here, way of life. We cannot have spaces. There's no space. Way of life underscore life lifestyle one. That is the code. So we coded it as way of life lifestyle one. That's the code for the effect variable way of life. Copy the original source of the survey, paste it here, and then copy again. Be religious on not making shortcuts, way of life 2, and then go to the original source, copy, and then paste. Go to the way of life code name, paste it here, make it number 3, go to the original source, copy, and then paste. Next, copy, and then finally the original source, paste. All right. So we have 1, 2, 3, 4 surveys. We're gonna go to the values, copy, and paste it. The survey for the code way of life lifestyle as an outcome variable of way of life as a lifestyle as only 4 surveys. The next outcome variable is called exercise as a lifestyle. So we're gonna put here on the code exercise underscore lifestyle one. All right. Go to the original source, copy, and then paste. Since this exercise is only a few, about 6, we can have that copy, paste. Let's count 1, 2, 3, 4, 5. Sorry, not 6, 5. 5, exercise lifestyle, 5, paste. 3, 4, and then paste. 5. Remember that the original source must be exactly the same. And so you have to copy the original source of the survey where the online survey question was found. And then I'll just copy and paste it here. Copy and then paste it here. Copy and then paste it here. Okay, we're gonna go to the next outcome variable called sleep pattern. So we're gonna go to the code and make this code called sleep as underscore pattern underscore lifestyle one. Okay, I'm gonna go here, copy. Oh, sorry, I said we have to be religious on copying the values and then copy that and paste it in. So if the values are complete, and we're gonna go for sleep pattern, the lifestyle. Copy this, go to the sleep pattern, paste, sleep pattern, paste, second, third, fourth, fifth, and then six survey questions, six code names for the outcome variable called sleep pattern is a lifestyle. The effect variable or dependent variable or outcome variable must be six here. Original source, copy, and then paste. Go to the original source, copy, and then paste. And then go to the original source, copy, and then paste. And then go to the original source, the last one, copy, and then paste. And then copy this, highlight, and then paste. Okay, so all of these are not nominal, but they are ordinal scaling. From the I follow specific to the ordinal, you can click ordinal, ordinal in the order of, right? That's called in the order of. All of these are ordinal because it's the order of from agree to disagree, from strongly agree to strongly disagree. That means 1, 2, 3, 4 orders has to be in chronological order. That's what's called ordinal. So the nominal can be numerical in which order you wanted to put it. That's fine if the ordinal is yes or no. Don't forget to save your work from the downloads, hypertension, and then click save your work, religiously save it. If not, then it's gone when the battery of your computer goes out, then you're so in trouble. Okay, so this is the input. Okay, and we're gonna not gonna touch that because it's basically an input. All right, so we have successfully done the variable view. This is called the variable view here. And now we're gonna go to the data view because we're gonna change these string words into numeric later after we have converted all the numerics into numerics. And what we're gonna do is go to the icon data view, and as you can see, all these are in words, and we do not accept words. The values are numerical, and therefore we have to change it into numerical view. So now we are here on the SPSS data view, and we are done with all these variables. We have completely done all the variable view. All we have to do is change these uh, control experimental into 1 and 2. Remember what is the control, what the value is the control, and value is the experimental. 1 is control, 2 is experimental. Go to your variable view first, and then remember the codes the values that you have placed. One is control, two is experimental. So all we have to do is go to the analog transform. This is the transform icon. Okay. And then go to recode into same variables, not into different variables, because if you could recode it into different variables, it will end up here on the next empty space. If you put it recode into another variable, it will add up here. And you will still have the string words there, and we don't want any more string words. We just want to have the numeric, but don't worry about losing all the string words because you have the Microsoft Excel. You still have a copy. This is an SPSS software, and we do not want words. We want it numbers. You can do it in the hard way, like one, two, one, one, two, 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 two. You can do it the hard way like this, but what if it's 168? And you don't want that. You want the easier way to do it. What if you missed? That's the question as well. What if you missed one of those? Then you're in trouble. So all you have to do is go to the recode into the same variable so that it can change from the same variable. And we're going for the groups. Click the highlight on the groups. Group, go here, and then click old and new. And then it has to be the same value. Value of the old is experimental and control. So let's try to copy the experimental and control first. Experimental and control. Okay, let's go to the original source so we can copy experimental and control. Now we're gonna go for the original source. So open to the transform, recode into the same variable, click group, highlight here, and then put it here on the other side, and then click the old and new labels. This is the old and new labels. Click this, and then recode into the same variable, but get the control first. Copy, and then paste here the old variable control. The new, there's two. First is the old value, and the next is the new value. The new value will be the number. Remember the number 1 for control. Okay, and then click add. Next is the experimental. Go to the original source, and then click here, paste experimental, and then value will be 2, and then click add, and then click continue, and then click OK. So as you can see, all these string words becomes number magically, and you did not do it the long way, 1 2 1 2 1 2 1 2 1 2. So it's very difficult if it's 1 2 1 2 1 2. And we're gonna go to the data view window because the next few icons and variables will be a lot, which is called um, the age. There's a lot, so we need to go to the age at the variable view, and remember what is the number 1 2 3 and 4 here, and you can enlarge it, lengthen it a little bit so that it gives you more space to read what is, which is which. All right. And 1 2 3 4 must be remembered religiously from the original source. That's why I told you you don't confuse yourself, but rather be religious on the chronological order of one, two, three when you're doing labels, values of the values of the labels. Recode, go to the transform again. This is going to uh, we're gonna click the transform icon again, and then um, we're gonna go to the original source. All right, transform, recode into the same variable. We are done with the group. Leave the group here so you will know which ones you have done already. Then click the age and click the old and new variable. Okay. Remember that number one is 20 to 30. Be religious, copy from the original source, and then paste it here from the old values. And then number one is the new value. The numerical value will be number one. One, click add, go to the original source, and then this is number two, original survey, copy it. Be religious in copying, don't type it down. So errors will be lesser if you have the original source to be copied on, especially if it is into languages. Number four, add, and then continue, and then click OK. After you've done clicking continue, you click the OK button, and then warning, it will be recoded. Remember, there's a warning. Okay, recode specified. So click OK. And let's go to the one that we have recoded. Okay, see the data view. All right, all of it has been recoded into a number. So as you can see, it's so easy. And all you have to do is do it again. Go to go to the variable view and see the male. Male is the first one. That's the number one. And then record it same variable. Okay, remember to copy the original source. Do not forget to be religious in copying the original source. And do not forget to be looking at the variable view. What is the value that you have done? Your value is one male, two female, and you cannot forget that. You cannot make mistakes on it because it won't reflect on the recoded the same variable if you have transformed it. Okay, so the transform icon will help you transform the string words to numerical. Click the old and new variables and then get the original source where the old value is found. Number one old value male should be number one for the new value. Click add and then copy and then paste. Number two, add, then click continue and then click OK. Just if there's a warning, say string variables can be recoded different length and recode may be inappropriate. Just click OK. And then the recoded exceeds the length of some of the variables. Just click OK. And then let's see if it is successful on your data view. Successful data view. Good. So 167 has been recoded from string words into numerical. So next will be body mass index. Okay, let's go again to the variable view and see the values of the variable view. This is the variable view. Remember, variable view icon. Just we double check the data view. It becomes numerical from string to numerical. And we need to remember what is the value for the body mass index as the next variable view that we'll check. So 1, 2, 3 are the values, and we have religiously done it here. So we have no problems of following a chronological 1, 2, 3 slightly obese. Transform, compute, I mean recode into same variable icon, and then highlight the body mass index from the box here, going to the string variable and clicking uh, the the old and new values, body mass index, old and new values, copy exactly what's found in the original source from the old value and make it new for string words to numerical. Number one, slightly obese. The original source is copied, and then click here, paste here, and then put number two, original source. Copy the original source and paste here and click number three. Okay, so these are the 1, 2, and 3 icons. Okay, and then click continue and then click OK. It says here different length. Okay, and then check again. We're gonna check again. Okay, let's see the data view. So we are so successful on the demography number 4. We see what we have. We already have string, we have a numerical instead of string. Demography 1 is numerical, demography 2 is numerical, demography 3 is numerical, and demography 4, which is the body mass index, became numerical. We did not put 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. It just automatically 167 times changed into 1, 2, 1, 2, 1, 2. All right, now we're going for the next demography, which is the marital status. Let's go again to the variable view, and we have to be accurate with the numerical values. 1, 2, 3, 4, 1, 2, 3, 4 here. 1, 2, 3, 4 must be found here. Okay, and go to the transform icon. We are going to transform it again here, transform from string words to numerical. Recode into same variable and click the marital status, highlight, and transfer it to the string variable. Old and new variable must be highlighted, copy the original source, paste here, and then click one, add, copy the original source, and then paste here, and then click two, and click add. Copy the original source, paste here, and then click number 3, and click add. Copy the original source, number 4, click add. Continue, and then click OK, and then again, go to the data view and see if it's successful. Okay, demography 5 is complete. All of it is complete. So that's what we have done. We have converted it from numerical, from string words to numerical. Go back to the variable view, and we are now going for the easiest part, which is called the outcome variables for the main survey. The outcome variables have code names, and all we have to do is put all the code names here on the transform, and then we are going to transform. So go to the transform icon, click this icon again, transform, and then recode into the same variable. So all we have to do is put all the variables here, highlight this and shift and then arrow down, and then put everything here and put recode old and new variable. So the old variable will be strongly agree here, strongly agree. And then the old value strongly agree will be number one. Add here. This will be strongly agree number one. Then the agree is number two. Copy the original source. Agree is number two. Add. And then disagree will be number three. Paste. Three. Add. And then strongly disagree. That's number four. Add. See here, as we can see, it is also written here. The number one is strongly agree. The number two is agree. Number three is disagree. And number four is strongly disagree. So we have placed it here from old to new values. All of it is the same. That is why it's recommended for you to make a survey questionnaire that has the same values if you want faster transformation of string words to numerical. Click continue and then click OK. Just if there's a warning, just click OK. If it says here the shorter values will be padded with blanks for comparison, just click OK. And then let's go and check the SPSS if we are successful on the data view. As you can see, everything here is already been converted from numerical, from string words to numerical. There are no more string words. Congratulations to us. So we're going to check what we have done on the SPSS. Here is the SPSS and voila, all of it became numerical. So what we need to do next for the 167, we're gonna go for the variable view. We're gonna click the icon, this window, variable view again, and we're gonna go for changing all these string words into numerical. And all you have to do is click this icon, and you will find three dots here. All right, the three dots will be evident here. Let's click it and then change the icon string to numeric. It has to be numeric. All of it has to be numeric. Click OK. The width, it doesn't matter because it's only numbers. The width will only matter for words, not for numbers. So if it's numeric, 3 widths, 4 with decimal places has none. All we have to do is click OK. If it says that some values of labels will be missing, it's okay. Just click OK. Then copy it and then highlight all these and then paste it. Some values will be okay, and then click OK. OK, 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 OK. Everything is okay. Click OK, 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 OK. There, everything has been changed into numeric. Don't forget, save, go to data view. It has already been transformed from words to numeric. Okay. And then click save. Always save your work. Religiously save it. And what we're going to do is we're going to go to analyze. This is the analyze pane or icon. Just click that and go to scale reliability because we want to see if all the items are reliable. So Control A and drag it here on this on the side and click the statistics. This is the statistics icon. Click this and then click item scale if item is deleted, and that's it. Click continue. No tests necessary. Just click continue, and then the alpha will show us whether It's more than 0.7. Like, okay. So it says here that the reliability that we have is 0.9, meaning it's highly reliable. And you know that the 37 items of your original survey questionnaire is highly reliable. That means what you did on your survey questionnaire has no ambiguity. Ambiguity means confusion. That means it's so relatable, it's so understandable, comprehensive, and appropriate for the respondents. Because the higher the Cronbach alpha is from zero point 0.7, highly reliable, to zero point 0.9 will be acceptable survey questionnaire, especially if you have newly redone the survey. If you are very, very new on that survey, you have originally formulated that survey, you have to use the Cronbach's alpha. So congratulations, and you are done with your survey questionnaire, and the SPSS says that your 37 items can be used in full-scale research. And if you use that in full-scale research, you can continue on. There's nothing to change. Everyone has understood it properly and concretely, comprehensively, understandably done your survey appropriate, your survey is reliable. We can count on the results. There are no contingents, conspiracy, and ambiguity. That is the word ambiguity. There is no ambiguity because it's reliable. Congratulations. So the question is, what if I have done on Microsoft Word document, printed it and distributed it without the online, the classical way, traditional way of doing it, not using the Google Online survey form, but I use Microsoft Excel, and it's also bilingual. We're going to go for um, the next style of doing the SPSS, transferring it to the SPSS. So we're going to transfer all these into the SPSS. We're going to go for the data view and variable view. So we have to put here the name, variable view. Okay. Um, and from the original source, we'll put here demography one, and then put here on the label, okay, 18 to 24 years old, copy. You don't need to get the second language. Why? Um, you don't have to, because you're gonna do it the long way. Paste here 18 to 24, and it's not gonna be converted to string to numerical. So no need for you to copy the second language. This is number 3, add, and then 36 years of age. Um, it's it's number 3. This is number 4. Sorry, number 4. Okay, this is the long way of doing it, but this is the other way of doing it. So demography 1, demography 2, numeric. It has to be numeric. The numeric type is here. This is a good one. If it's string, you change it to numeric. So the demography number 2 is called gender. And all you have to do is copy it. Male, women, or male. Number 2 is women. Click OK. So both this will be um o- ordinal, nominal. Both will be nominal. And then the demography number three is total family income. Demography three is total family income is less than 3,500. That's number one. Okay. Add number two. Copy to paste here. Add. All right. C. We're not letter C. Copy. That's value number three. Paste here. Add letter D. 14,000. Value number four. Paste here. And then letter E more than 21,000. Remember that you do not need to get the second language. Okay, click OK. And then again, this is nominal. Uh, Another variable called basic nursing graduation. Okay, so this is still demography. It's the year. Demography 4. Based your basic nursing graduation year. So 2020 to 2024. Copy. One will be 2020 2024. That's the year. Number two, 2015 to 2019. Number two, 2019. Number three, that's 2010 to 2014. And then until 2010. That's number four. Letter D is number four. Okay. So this will be the main survey or effect or outcome variable number one. What's your main reason for choosing careers? Let's put career, career one as the main outcome or dependent or effect variable. And the question is what's your main? Copy this question from the original source up here. So copy this love of nursing. Copy. This is number one, paste here. And then occupation, prospects, copy. Number two, paste here. And then influenced by friends. Number three, paste here. And then economic stability, copy. Number four, paste here, add. Letter E is others, please indicate. Number five, paste. Okay. Next is what motivates. Career number, career two, this is called career two effect variable, career two. What motivates you into nursing? I'm here, paste, right? Career advancement, copy. Label one, paste, add. Higher salary potential, paste, add. Personal learning, copy. Number three, paste. Add, wants to specialize in a particular field for paste. And then add pressure for society. Number five is add, doesn't want to start work early. Number six is add. Click OK. Then we go to career number three. Career three. This is the code. We're just doing it as a code name. Question is, what challenges do you foresee for your bachelor's degree? And you have to copy the original source, put it here, paste. Okay, value one, economic stress, copy, and paste here. Letter B, time management issues. So this is number two. Letter B is number two. And then academic difficulty. So this is number three. Letter D is work-study balance. Number four. And lack of family support. Number five. And then click OK. We have a number four, career. Effect variable code name number four is career four. So what challenges is career three? The next is, are you interested in pursuing bachelor's degree in nursing? Copy the original source, paste here, and then put value one, yes, value two, which is no. Okay. This is the only scale. Okay, yes and no is a scale. The others are all nominal. All of these are nominal. It is not in the order of. Okay. The yes and no is usually a scale. Okay. Next is career number four. Number five. Career five, code name for the effect variable or outcome variable with a survey question label of, if you are interested, when do you plan to start studying? Okay. Letter A is immediately after graduation. That's number one label. Immediately after graduation, within 1 year, copy, paste here. 2 to 3 years, copy, paste here. There are no definite plans. Before, copy, paste here. Okay, then click OK. All right, there's a number 6 question. Career 6. Would you consider studying nursing abroad? Paste. So label number 1 is yes. And label number 2 is no. And this is called a scale. And the other one is nominal. Oh, there's a probably. So it's not a scale. If there's a probably here, There's a number three. It's not a scale, but it is also a nominal. Nominal. It's not in the order of. So it can probably can be one, no can be two, no can be three, yes can be four, and yes can be one. Okay, so that's what you call nominal. You can nominate which number is what you prefer. It's not in the order of. Career 7 will be the next code name, and the original source asks the survey into the label as if so, which region would you prefer? Um, Northern region. So these are the values. Okay, go to the values. Put here number 1. Original source says north, and then Europe. So a nominal can be Europe can be number 1 or Asia can be number 1. There is no order of, it's not in the order of. Okay. So the north can be the last, doesn't have to be number 1 because it's not in the order of. That's called nominal. And then others. Paste. List number 5. Click add. Click OK. That's it. Only 7 outcome variables to be measured, 7 effect variables. And we have completed the variable view. We're going to go for data view because we do know what to put on the data view. So first is the demography. It says here, how many demographies do we have? Demography number 1. You can expand this so you can see what are you looking at. What is your question? What's the code that you're looking at? Okay. And if this is the demography 1, we're first on the demography 1. How many 18 to 20 years old? 4. So 1, 2, 3, 4. 4 ones and 2 twos. So 2 twos. And then how many 3? 3 threes. Okay, 3 threes. 3, 3, 3. And then how many 4? Only 1 4, so 4. So the total is 10 respondents. There are a total of 10 respondents based on the original. There's says here 10. These are the total respondents. On the demography 2, how many ones? There will be only 1. This is 1162, and the 3 threes. 6 twos, 3 threes. Okay. How many ones? 1. How many 2 6? 1, 2, 3, 4, 5, 6. And then how many threes? Will be 3. 1, 2, 3. So we go for the demography number 3, which is called total income. How many ones? There are 1 ones, 1 ones, 2 twos, 2 threes, 4 fours, and 1 5. Okay, so there are 5 values. How many ones? 1. How many twos? 2, 2, 3, 2 threes, 4 4 fours, and then only 1 5. Okay, same goes with the demography number 4. Basic income 1 1, 2 2, 2 threes, 4 fours, and 1 5. 1 5. Okay. Next is the effect or the outcome variable. I think the demography 1 2 3 4. That's right. Oh, we made a mistake. Okay, 1 ones is not the same. This is the basic nursing. three ones, one, two, three, and four twos, one, two, three, four, and three fours, three threes. Okay, three threes. One, two, three. That's it. Zero for number four. So we're gonna go for effect variable number one, which is career. This is the hard way because you can make errors. What if you have 150 respondents, 160 respondents? It'll be so difficult for you to decipher how many. But this is the long way of doing it. The effect variable number one, which is career one. What are your main reasons? There are A, B, C, D, five values, one, two, three, four, five, and number one is two. Two values for number one, two values for number two, and five values for number three. One, two, three, four, five. And there's one value for number four, and there's no value for the number five option. And then the next, which is career two, what motivates you? One. So there's one, two, three, four, five, six options. So there are six values. And the first option is one. There's only one who gives six, the first option. And there's three for the second option. And there's four for the third option. And there's one for the fourth option and one for the fifth option, totaling of 10 respondents. We are lucky we have only 10 respondents, so it's easy for you to do it this way. What challenges do you foresee for your bachelor's degree? Nursing is career number four. Career number three, code name career number three. For the effect variable, outcome variable, what challenges do you foresee for your bachelor of nursing degree? And there are five options or five values. So one for number one for number two, five threes, one, two, three, four, five. And then work study balance, which is number four. There are three options for number four. There are three respondents for the fourth option. We're gonna go for career number four, which is called are you interested in pursuing bachelor's degree in nursing? And there are yes, no, and there's no definite plan. Okay, there's three variables on career four. Career four, let's go back to the variable view. It is not a scale. Are you interested? It's not a scale, but rather a nominal because there's a number third option. Third option is there's no definite plan. There's no definite plan. Add here, click OK. Change the scale into a nominal since it is not a scale, but rather a nominal. So there are six for the yeses, six number ones. One, two, three, four, five, six. And there are three no's, three for number two value, three, and there's one for one value. We're going to go for the fifth code name called career five, and the outcome variable is called if you are interested, when do you start planning? So number one is immediate after graduation. We have four values because we have four options. So the option one has three respondents, one, two, three. And then the option two has two respondents, two, two. And then the option three has three respondents, three. And then the option four has two respondents. Okay. Go for the sixth career, which is called the code name. Career six is code name. The outcome variable is called would you consider studying for bachelor's degree in nursing abroad? Yes, no, probably. So the yeses is number one option. There's option one value one, four times one, two, three, four, and then value two is one, value 3, which is probably is 5 times 1, 2, 3, 4, 5. And then the career 7, which is code name for the outcome variable number 7. If so, which region would you prefer to study in? North, Europe, Asia, Australia, others are all nominal. It's not in the order of, but it's just nominal. So option 1, value 1 has 1. Value 2, option 2 has 2. Values 3, option 3 has 6. 1, 2, 3, 4, 5, and 6. And then the others, and sorry, 1, 2, 3, 4. Fourth value is 1. There's one value for number 4. Thank you very much. We are done with the data view. Okay. We're done with the variable view, and we need to get the convex alpha. The alpha has to be more than 0.7. Okay, we're now at the data view, and we're gonna go for the analyze, right? Click analyze, click scale, reliability, control A, click the arrow, click the statistics. Okay, and then we'll click the item, scale if item is deleted, and scale. Click continue and click OK. And then we're gonna go for the output. This is the output document. This is another folder that will appear. And as you can see, the 11 items are all reliable. That means it's not ambiguous. There's no ambiguity. You can count on it. No confusion. Comprehensible, understandable, appropriate for your title, and the respondents can respond. Can they respond? If they respond, can you rely on it? Because it's more than 0.7, the answer is highly yes. All the 11 items are appropriate. The respondents can respond, non-ambiguous, comprehensible, understandable, appropriate. You can continue on with your survey. However, remember that this is the long way of doing it. So you choose whether you want to use the online survey form with a lot of respondents, or you want to do it with manually doing it on the SPSS, because only the SPSS have the alpha Cronbach's alpha. As you can see, this is called the Cronbach's alpha. And therefore, there's no other device or software that can give you the Cronbach's alpha. Thank you again for listening for a lot of hours, and I hope you learned something for the measurements of the Cronbach's alpha for the reliability of your newly devised survey questionnaire. We only do this for the newly devised survey questionnaire. If you want to do this as well for the revised edition or adapted edition, that you just simply remove some of the settings, you put some of the variables, the outcome measurement variables, you change it. It's the adaptation of a questionnaire from somebody else, but you just revise it. You need to do the Cronbach's alpha as well, even though it came from somebody else. It has been reliable, researchable, but you change the setting, you change the variable icon for your measurements, for your adapted survey questionnaire. You change it to China, you change it to the Arabian setting or appropriateness of the respondents in another setting. That needs reliability tests called Cronbach's alpha test. And the survey's SPSS must be done again. Thank you very much for your time. Thank you and all the best. Hello, everyone. We're going to discuss first about descriptive and how to use your SPSS. So The first thing is to look for frequency and percentage, and that's your first task.
So I'm gonna go to my output window. So I don't want to exit and enter and exit and enter again because I'm sharing the screen. So just gonna go to my output window and I'm gonna click analyze. I'm gonna click descriptive and I'm gonna click frequencies. Okay, I want to see the frequency of everything, you know. I'm gonna shift down and highlight everything and put here on the variables everything that I have done. Okay, and I'm gonna go to my statistics. I want to see the percentage, so I want to put here 100%. Okay, that's my percentile, and I'm gonna click continue, and I'm gonna click OK. What am I showing now? What window am I showing?
Frequencies.
What?
Okay.
Frequencies.
Okay,
Okay.
the OK button. I'm in the OK button, right?
Yes.
Okay, I click the OK button. So all of this came out. All right, all of this came out. So what I'm gonna do is I'm gonna highlight all these. I'm gonna highlight this one by one, and I'm gonna copy this and go to my uh, Microsoft Word document because I don't want to use tables. But you know, you can, if you're artistic, if you're doing the art, you can put there the color because it's so colorful. You see, it has blue, light blue, aqua blue, red, orange, green. You know, there's a lot of spectrums of color. But since I only want numbers, I want to see the percentage of how many descriptively. I'm gonna click that descriptive and I'm gonna remove all this, and this will be changed a little bit. Okay, it has to be adjusted. Okay, so this is the work experience. Okay, so this is the validity. Okay, and again, I'm gonna put more. It's not finished yet. I'm gonna put more from the SPSS. All right, so I'm gonna go back to my output SPSS. This is my work experience. I'm copying the work experience field of work. I'm gonna copy this and I'm gonna go back to my Microsoft Word document. This is my demography too, and I'm gonna paste it here. So I have two demographies, and I don't need this valid percent and cumulative percent. All I have to do is show me the percent and frequencies. Okay, I'm gonna put this here, all right, and I'm gonna cut this and put this here in the valid box. Okay, I'm gonna cut this. I'm gonna put this here on the valid box. So these are my two demographies, and I'm gonna combine these together as one. All right, adjust this. All right, adjust this as I wish. Maybe adjust this a little bit further here, adjust this a little bit further there, and adjust this a little bit further here. Okay, and adjust this a little bit further there. There, I have my this is my table called demography. Table 1, demography. Okay, so this is my frequency, N. Okay, and this is my percent. All right, this is my percent. All right, so that's it.
Now that we have learned a lot of the basic analysis, for example, you have already keyed in years of work experience here on your variable view over here. And you have already placed the label and the values for the years of experience and job satisfaction. The first task that you must do is to go to analyze here and click the normality test because we need to see if it is normally distributed. And in order for you to go to the normality test, you have to click the analyze, descriptive statistics, and then explore. Okay, so um, you will find all these basically here at this side of the table, and you have to transfer it to the dependent, which is the effect variables. You're looking for both effect variables. And you have to click the plots and remove all the other ticks that you find. Only the normality plot will be ticked here. Only this, because you just want to see the normal distribution. Click continue, click both uh, S statistics and the plots, and then click OK. And we are going to see the output. So these are the outputs of the job description. And as you see, we have to look for the Kolmogorov, Smirnov, and Shapiro will. And because it is less than 0.05, both Kolmogorov, Smirnov, and Shapiro will are not contradictory of each other and stating that this is not normally distributed, not normally distributed. So it is not normally distributed, and therefore it is non-parametric test. And, and we have to choose the non-parametric test. So how to decide which non-parametric test to choose from? We have to go back to the main SPSS and look for the variable and see the values. Okay, if the categories of the values, regardless if it's nominal or ordinal scaling, if there are three or more categories and of both what you're trying to compare with, there are three or more categories, you must use the Kruskal-Wallis test. So Man-Whitney test is for categories that are two, but we have more than three categories here for both the years of experience and job satisfaction, and therefore we need to use the Kruskal-Wallis test. So let's try to test it using the Kruskal-Wallis test. And we have to go to the non-parametric test on the analyze, and then go to the legacy dialogues. It's better if we choose the output. Let's try to go to the output. This is the output, right? So that it marks where we have done the latest. Go to the legacy dialogues and then go to the K independent samples for the Kruskal-Wallis test. All right. Uh, you're testing the variable. You can alternate the variables. If you're testing the years of experience variable, that is your most preferred, then your grouping variable will be the satisfaction. All you have to do is define the range, whether it's minimum one or maximum two. You can either do both, and then you have to take the Kruskal-Wallis test to get the mean and the standard deviation, and then click OK. So you got the mean and the standard deviation here. It's so obvious, and the quartiles are found here, which is not really important for you to take to note with. So the years, you can now make an inference or a diagnosis that the years of experience had 1.98 plus minus 0.7. Sorry, it's not 7, it's 0.7. Plus minus 0.795. Okay. So the years of experience had a mean score of 1.98 plus minus 0.795, while the job satisfaction had a mean score of 7.52 plus minus 1.69320. And that's how you make an inference. So the job satisfaction has a larger difference of their deviation as compared to the years of experience with lesser deviation from the mean, from the center, which is the mean. And that's how you do your first interpretation for non-parametric tests. Now, since it is not normally distributed and it's non-parametric, you want to know what is the relation, is there a relationship between years and job, years of experience and job satisfaction? You may use the Spearman rule because it is non-parametric, so the test will be Spearman rule. So we're gonna go to correlate and bivariate, and then you will usually find it here at the left side. Okay, so all you have to do is transfer it to the right and then click the Spearman Raw, not the Pearson. A correlation of non-parametric is Spearman Raw, not the Pearson. And therefore, we will find the answer to the question to the significance. Okay. If it is greater than 0.05, then it has no relationship. Therefore, regardless of how many years you work, you can still not be satisfied. Or irregardless of how many years you work, you can still be satisfied with your job. And irregardless, it can be vice versa. Irregardless of how much satisfied you are, it doesn't matter how many years you work because there is no relationship between the two. So both are not related to each other. And that's how you do your non-parametric tests. And usually non-parametric tests will only be for lesser than 50 participants. As you can see, there are 50 respondents to this. And we usually have a not normal distribution on lesser number of samples. And if we go to a bigger number of samples, we'll try to see bigger number of samples on another test. I will show you a bigger number of sample. And this is an example of another SPSS. And if you want to see how many you have to drag down, how many respondents do we have? Drag all the way down, and you will find that there are 80 respondents. Okay, so the bigger number of population here. And if you want to know the variables, you can see that there are post-test and pre-test intervention and control. So basically, it's divided into two groups, intervention and control. And if you have two groups of 80 respondents, that means this is 160 in total. None of these intervention can be in the control and vice versa. A control can never be an intervention and an intervention can never be a control. So if this is an 80 participant and has two groups, and therefore they are called a cumulative of 160 respondents. So they are definitely normally distributed. on both ends. And if that is so, and we have to analyze it based on a parametric test. And if you want to know the relationship between intervention and control group for a parametric test, you need to use t-test. But since this is a separation of uh, post-test intervention, post-test control, pre-test intervention, and pre-test control. There are two questions that we want to know whether it's control, both post-test control, or both post-test intervention, or both pre-test intervention or pre-test control, or only intervention and control, either post-test or pre-test. Neither will matter as long as it's an intervention group. We can have both in the transform variable. So all we need to go to is transform them from here. Go to the compute variables and find the post-test. You can actually make this bigger so you can read the whole thing. Okay. Since it needs to be the whole table, so you will know whether it's pre-test control or pre-test intervention. So let's start with the first question. Is it significant for both interventions and control? Intervention only, whether it's pre-test or post-test, we're going to use intervention group. That's the name of the target variable. So all we need to do is get the accumulation of all the intervention groups, whether it's pre-test or post-test. Go to the next group, post-test intervention group, because we are now targeting only intervention, and then click OK. So that's intervention group. Okay, let's go back to the SPSS. We're not done with the question. And the next question is the control. So we're going to change this target variable into control. Here we have changed target variable from intervention, it becomes control. And therefore we have to remove this and then see again. We have to get only the control group, pretest, pretest control plus post-test control, post-test control. Okay, then we have to click OK. And we go back to the SPSS. All right, so we have two groups. Now we can answer question, what's the difference? We're going to use the t-test. And there's another question that we wanted to ask, whether post-test of both control and intervention is better than the post-test of both um, intervention of a pre-test intervention and control. So we're going to have the transformation again, because our next question is only pre-test. Pre-test. We don't know whether the pre-test works, whether the group before the intervention is better than those who did after the intervention. Pre-test intervention group. Only pre-test we want to see. So that's the transformation that we're going to do. All right. Let's try to do another sharing, because we have another question in mind about the post test. Maybe the post test is better, after which they have done their own interventions, or the control has done its own conventional way of doing it. So let's do the post test. Post test control plus post test intervention. And if we click OK, yeah, we now have an accumulation of all these transformation. So now we can have an analysis based on our question. We have to go to analyze, and then we will go to compare means and paired t-test. Okay, the first question that we have is, who's better, intervention or control? That's the first question. We were also asking whether pre-test or post-test, which one is better? And we can also ask another question, whether pre-test control is better than pre-test intervention. We can have those questions here. Whether the post-test control is better than the post-test intervention, because it's very interesting to know whether which one is better, the post-test intervention or the post-test control. They have both the intervention. Some one is doing conventional and the other one is doing the intervention. Or better, anyway, pre-test intervention and pre-test control has no value because it's before the intervention, and therefore none of them has any idea of what's happening. So it's not interesting to know that anymore. Only these three are interesting to know because they are a combination of. So let's click the OK button. Okay, there are three groups, and oh, this is a good one. There's a very big significance, and if the significance is less than 0.05, then the hypothesis is accepted, or maybe the null hypothesis is rejected because the significance is 0.05. So if you're asking whether uh, post-test and post-test have a significant difference between each other, yes, the answer is yes. And since this is a parametric test and we want to know the relationship, we can see the relationship here. This is the significance, right? And these are the questions that we're looking for. They're asking these questions. Are they better than each other? Are they better off with each other? The answer is yes. You can reject the null and accept the alternative hypothesis. Now, we want to know if they have relationship with each other. So we're going to go to the analyze, and we're going to go to correlate and bivariate, and we're going to choose the Pearson correlation and no more the um, Spearman row, because this is a parametric test. We can now look for the intervention, whether it's related to the control group, right? Do they have a relationship or not? And just click OK. The answer is yes, they have a relationship with each other. Um, that means the conventional way of doing what the variable needs to be done, as compared to the new intervention that has been administered or has been um, presented, is correlated with each other. They have a relationship with each other. All right. And then the next question, maybe we're so interested with the next question between the pre and the post. We're going to analyze, bivariate, all right, all the way down. The pre and the post, bring this back there. We cannot have four on Pearson correlation. Pearson correlation, only two. So it's so interesting to know whether the pre-test is related to the post-test. And the answer is yes, because the significance is 0.0000. Therefore, there is a very good relationship between the two. And that answers the question of pre and post test. So one of the factors that you need to remember is when you go to the variable view, and if you're looking for a non-parametric test, you have to see the categories or the labelings of these. If it's too categorical and the category is yes or no, you can use the man with new test, not the Kruskal-Wallis test. So that's one of the basic things that you need to remember. And just be careful when you're trying to use categories, because some of the categories may be similar, although some of the categories are similar to each other, like this obedient or disobedient, yes or no, they're both similar to each other, and the category is only two, then that means you need to use man with new test. And if you have three categories here, don't combine this with the two categories. It will have a contamination of the results. So when you're trying to make and formulate your own questionnaire, survey questionnaire, just remember when you're trying to combine and transform them together, there will be contamination of the results, and the results may be unreliable. Looking at unreliability, because it is discrepancy between the two. So just be careful on the categories that you're using. And remember that the order of is different from the scale and the nominal. Nominal is numerical and it's not in the order of, and there's a difference between in the order of and not in the order of. So those are the things that you need to remember. And I hope you learn how to make your survey questionnaire, since that will be one of the most uh, critical thinking tasks that you will need to remember when you're trying to make a survey questionnaire. If the SPSS will have contaminations or discrepancies, then the results are unreliable. Make sure that your questions must have a reliability test, whether you can count on it or whether it's confusing and ambiguous, since it is contradicting to the theories that you have learned from all these.
SPSS to determine if a variable, a continuous variable, is normal or not. We're going to go ahead and use the Kolmogorov-Smirnov and the Shapiro's Wilk test. So it goes fast. Let's watch. We're going to go to Analyze, Descriptive Statistics, Explore. We'll kick all three of them in there. We're going to go to Plots. Don't use stem and leaf. I normally do the histogram, even though it can be misleading, but here's the main one: normality plots with tests. Okay, that's going to bring up the Kolmogorov and the Shapiro-Wilk. Click, click, click. And there's our first box. There's the descriptives. And here's the Kolmogorov-Smirnov. These first columns, right? 1, 2, 3. These are the KS tests, Kolmogorov-Smirnov test. And then the next three, 1, 2, 3, the Shapiro-Wilk. Normally they agree, okay? Normally they agree. They don't always agree. So researchers tend to say if you got a big sample size, and they're not real specific on how big, but normally 2,000 or above, the Kolmogorov-Smirnov is more accurate. And if you got a small sample size, again, it's kind of gray area, which was considered a small. The Shapiro-Wilk is a more accurate. So Shapiro-Wilk normally, I found one book that said, 20 or less for the Shapiro-Wilk. Anything over 20, you should use the Kolmogorov-Smirnov. But again, like I said, they usually agree. The Kolmogorov-Smirnov test, it has a little special thing. Some of these things you'll have a little asterisk, and the significance will be 200. What that means is that the software is calculating that if you had a bigger sample size, then the data set would probably be normal. That's what that means, okay? But these are all less than 0.05, which means that anxiety variable violated the assumption of normality, as did depression and stress. In other words, none of these are normal. Remember, when you're checking assumptions, if the p-value is less than 0.05, in other words, if you get significance while checking an assumption, that means you violated that assumption. I'll say that again. Students get confused on this a lot. So think about the null hypothesis when checking assumptions, right? The word no or not is in the null hypothesis. So the null hypothesis would be these variables did not violate the assumption of normality. That's the null. They did not violate, okay? So you get to reject that, right? Because the p-value is less than 0.05, you reject the null. Therefore, the null becomes the alternative, which is true. The variables did violate the assumption. And again, this is why you don't go by the histograms. That one doesn't look too bad to me, but it's not normal, right? And this one looks pretty normal, but according to the Kolmogorov, Smirnov, and the Shapiro-Wilk, none of these are normal, right? So there is depression. Again, it looks pretty normal to me, but not to the math. That's what we got to go by. Now, this one does look skewed, okay? Okay, but that's it. And again, this is your box. Right there. So remember, if the significance is less than 0.05, it had violated the assumption. And that's true for all assumptions, not just normality. Last time, if the p-value is less than 0.05 when checking assumptions, that means you violated that assumption. All right, that's enough. MGZ out.
Is through Levine's test. And really, it's done for you automatically as soon as you do an independent sample t-test. So if you go into Analyze, Compare Means, Independent Sample t-test, and you put your dependent variable in the test variable box and glasses in the grouping variable, and then specify your groups that you're interested in. For me, it's 0 and 1. Click OK. You get a descriptive statistics table, and which is this. And then Levine's test is right here. Levine's test for equality of variances. And it's an F test, technically. And you get an F value of 2.359. And its significance level is 0.129. So I mentioned in the textbook that this is one of those rare tests where you're quote unquote hoping not to see a p-value less than 0.05. You're actually hoping to see it greater than 0.05, because that will imply that the variances are probably from the same population. And you basically, in order to do the t-test, you're hoping that's going to be true. Although, as I mentioned in the textbook, it's not a big deal because we can easily use the results associated with the equal variances not assumed row in the table if we do find a significance value that's less than 0.05 here. Now, in this case, we did not reject the null hypothesis of equal variances. They're not reported. We have the standard deviations, which are close to the variance, and we can see that it's 0.768 versus 0.813. Numerically, those are fairly similar, and that's reflected in the p-value not being less than 0.05. So that's how you can test the assumption of homogeneity of variance by the Levine's test of equality of variances in SPSS.
So I'm going to do those three different tests for homogeneity for Levine's. One's called Levine's, the other one's called the Brown-Forsyth test, and the other one's called the non-parametric Levine's test. And I've got another presentation video on howtostats.com YouTube's channel that's called Homogeneity of Variance, where I discuss these different tests conceptually, as well as other issues relevant to recommendations. I encourage you to check that out. So here's the actual step-by-step process for testing homogeneity of variance in three different ways, one of which is really good and really robust. I'm going to show us first the actual distributions of these data. What it is, I've got two groups, zeros and ones, and I've got IQ as a fictitious variable with scores. I think it's 20 in each group with IQ scores. Now, these data are actually fairly non-normally distributed, and we can check them out going through descriptives. And I've chose these data purposely Actually, one of them is more non-distributed than the other. So I'm actually going to split my file first according to group. Okay. So let's check out the distributions, charts, histogram, continue, and let's look at the standard means and standard deviation as well, or mean and variance. All right, so here's the just the basic descriptives that I'm looking at. And what we've got here are variance for group 0 is 216. And that's a fairly non-normally distributed distribution that I've seen. So there's a positive tail. It's not really, really skewed, but it's probably about a 2.5 or something like that. I can actually check in a minute. And here's the other distribution of data, which is not perfectly normally distributed either, but not quite as skewed as the other one. Its variance is 383. So the variance in this first group number 1 is larger than in group number 0, which is 216. So we want to test these for variance homogeneity. And what most people do is that they'll go into compare means, they'll go into one way. You could do this in a t-test as well. Actually, I'm not sure if it'll do the homogeneity of variance in t-test. I can't remember off the top of my head, but here we got options and we've got homogeneity of variance test. And this is actually going to do the traditional Levene's test, which is comparing, deriving absolute values from the observations and their respective mean. Again, check out that video that I've done. It's more of a lecture talking about these different techniques. I forgot to unselect my split file because I don't want to select these by group or analyze all. All right, so analyze, compare means, one-way ANOVA. Let's do that again. So here we get the test of homogeneity of variances. Now, isn't that interesting? It's not quite so statistically significant. And so we'd feel confident reporting our ANOVA F value, which is suggesting that there's no mean difference because it's not statistically significant and the F value is really small. Now, are these variances different or not? I mean, that's still the question that we want to answer. And based on the traditional test of homogeneity of variances with Levene's statistic, 3.906, it's saying that the variances are not statistically different from each other, although it's nearly so, but it's not quite. Now, that's how you do the traditional Levene's F test. Since Levene's published his paper first demonstrating it, there's been a couple of more slight modifications to the test, one of which is to use medians instead of means upon which to calculate the absolute differences. Now, I'm going to show you very quickly how I can actually replicate this Levene's test based on the means quite easily, and then I'll show us how to do it on the medians, and then I'll show us how to do it I'll show you how to do it on the ranks, which is the non-parametric, what's called the non-parametric Levene's test. I'll show you how to do it on the ranks, which is the non-parametric, what's called the non-parametric Levene's test, which is the most robust when you have skewed data. Now, to actually do a poor person's Levene's test, if you will, go into data and aggregate. You don't have to do it this way, but this is the way that I think is the easiest way. And I'm again going to have to actually calculate the groups based on split file because I need to get the means respectively for each group. Click OK. All right, and then I'm going to data and aggregate, and you're actually going to see the means form a variable. I suppose I could have chosen a break variable. Sorry about that. This is actually a better way to do it. I wonder if it would have, I wonder what, who knows? I'll have to try that again, see if it actually does the same thing, but I don't want to take a chance. So I'm going to do IQ and group, and I'll show you what this does in a second. It's actually quite simple, but so what it's done is it's calculated a variable called IQ mean, and it's calculated the mean for the group that's called 0, which is 102.9, and it's got that value for all of the values of 0. And then for the group of 1, where the mean is actually 100, it's created the mean variable, it's all the same variable, but it's actually segregated it according to its own respective means. That's a really cool feature in SPSS to be able to do that. So now I can actually compute the difference between the IQ values, IQ difference, let's say mean, we'll call it a mean because it's against the mean. So we'll IQ minus mean, and we'll click OK. And that calculates 91 minus 102.9 equals 11.990, and it's calculated that for everybody. And then it also does it for the ones, but based on a different mean, because the mean is different for the for group number 1 versus group number 0. Now I need to transform these into absolute values, and that's easily done too. And you just go like that, absolute, and put that variable in there, and then it's going to ask me, do I want to change the existing variable? And I do. So now I've got the absolute difference values for all my observations, but respective to each group's mean. And now if I do an ANOVA on this variable here, whoops, if I do an ANOVA on this variable, this is actually the Levene's test of difference for the means, but it's the traditional old-fashioned one. Let's check it out. I don't actually want to calculate homogeneity variance on that. See the significance level of 0.055 with an F of 3.906? Well, that's actually the same value that we got here. So that's what the Levene's test is, homogeneity variance. It's the difference, the mean, it calculates the mean difference between the absolute differences between each observation and its corresponding mean. Now, the problem with the means-Levene's test is that it's sensitive to variations in the distribution. So if your data are non-normally distributed, it tends not to be powerful enough. So in this case, where it's almost statistically significant, I'd be thinking, oh, well, and the data are non-normally distributed, maybe the Brown-Forsyth Levene's test will be better, which is actually using the median instead of the mean for the point of comparison upon which to calculate the absolute differences. Well, that's easily done too, because we just have to calculate that same aggregate variable. But in this case, I want to change the function from mean to median. And click OK. And that creates a new variable called IQ median. And now I can calculate a new difference score based on the median. Okay, so IQ minus IQ median. Click OK. So here it comes out, and now I want to calculate the absolute value for those differences. I could probably do this all in one command, but I'm just doing it in an easier way so everyone can see what's going on. So here are the differences. And now I just have to perform a ANOVA on these same values, which are very similar to the IQ mean value. So it's 11.9. Oh, actually, that's a fairly big difference. So I'm going to expect some a difference in the Levene's test based on the median, which people call the Brown-Forsyth test, unfortunately. I say unfortunately because there's another test called Brown-Forsyth, which is actually different to this homogeneity of variance test. And here we got, okay, so it actually didn't work out. It's not quite as powerful in this case. So it didn't come out to be statistically significant. So now we'd be feeling, okay, well, maybe it's actually robust to this level of deviation in non-normal distributions. But there's still one more type of Levene's test, which I talked about in the lecture or the conceptual discussion about homogeneity of variance, which is called the non-parametric Levene's test, which is actually based on ranking all the data first, get a rank on the pooled data. So rank these scores from the pooled data, and then calculate the mean difference between those ranks and the mean rank, and then calculate an ANOVA on that. So let's try that. So I need to transform my data into ranks is the first step for this non-parametric Levene. So IQ is going to be converted, well, a new variable is going to be created, and they're going to be ranks. So these are the ranks for the pooled data. I haven't split the data. These are the pooled whole sample size data. All right. And then I calculate the mean for those scores, or respective means, just like I did for the other Levine's test, or the first one. So data, aggregate, and mean, but I don't want actually that variable. I want this rank IQ variable. I'm going to click function, and I want the mean. Yep. And now I'm going to click OK. So now it's calculated a rank IQ score, which I did first, and now it's calculated a rank IQ score for mean for each respective group. Group 1, which came out to 21.8, and group 0, rather, 21.08, and group 1, which is 19.93. Now I just have to do an ANOVA on this new variable. Descriptive or compare means, one-way ANOVA, throw that out, and now I need to do this on the rank mean, RQ mean scores. Actually, I haven't calculated the difference yet. I need to calculate the difference between these. Sorry. Transform, compute, IQ difference, rank. So the rank score minus the mean of the rank scores. And now I need to get the absolute value for that. Transform, compute. Whoops. Okay. Now I actually calculate the difference between the mean differences between these two using an ANOVA, which is a Levine, it's called a non-parametric Levine's test. And it's the most robust and the most powerful when you're analyzing non-normally distributed data, and where your sample size might be unequal as well. So click on OK. And in this case, we do get a statistically significant effect. This is telling me that the variances between group 0 and group 1 are actually statistically significantly different from each other when analyzed via the non-parametric Levine test. And this Levine test, as I discuss in the homogeneity of variance, and I give references in the homogeneity of variance, it's a study by Nordsky and Zumbo that in a couple of papers have shown the utility of this non-parametric Levine's test. And it's easy to calculate, and it's very powerful, and it's less likely to actually commit type 1 and type 2 errors. So it's a great test all around. The only exception is when the data are when your data really are normally distributed, then you're better off using the traditional Levine's test.
First, recall that we interpret the results of our Levine's test. And as a reminder, the decision rule is as follows. If p is less than or equal to 0.05, the variances are significantly different, and we want to interpret the bottom row of results for t. Whereas if p is greater than 0.05, the variances are not significantly different, and we want to interpret the top row of results for t. Looking at these two conditions here, which does ours fall into? We have a p of 0.873. And that falls into the second condition here. So therefore the variances are not significantly different, and we'll go ahead and interpret the top row of results for t. So we're going to look at these values here in the top row for t.
Hello, I'm David Spade, and I would like to welcome you to Statistics 1, Linear Regression and Probability. We're going to begin this course with an introduction to statistics, basically just definitions of terms that are commonly used in statistics. So first of all, what is statistics? Well, statistics is simply stated the science of collecting data and analyzing variation in that data. And when we talk about data, what we mean is information pertaining to a group of individuals. Individuals can be human, plants, inanimate objects, websites, all kinds of different things. We have several different types of data. Data can be numerical, which means they have a numerical quantity as their measure. Data can be categorical, which means that the measurement on the individual represents what category that individual falls into. But regardless of the type of data, it needs to be presented in some sort of context. In statistics, we're typically interested in answering 5 questions, the 5 W's, who, what, when, where, and why. We're going to focus on the who and what. The who are the individuals on whom the data are collected. So individuals who respond to a survey are called respondents. People on whom experiments are conducted are known as subjects. And animals, plants, websites, inanimate objects, any other thing on which data are collected are known as experimental units. These are all whos. These all answer the question of who. The what simply refers to what is it that we're measuring. The what corresponds to the characteristics that we record about each individual, and these characteristics that we record are known as variables. Often, the individuals and the corresponding variables are a sample from a larger population. We're most concerned with finding answers to the who and what questions, so that's what we're going to focus on. So let's look at populations and samples. We mentioned them briefly during the what section. A group of individuals about which we want to make a general statement is known as a population. But in order to do that, it's typically impractical to look at the whole population, so we take a small group. And a group of individuals that are selected from the population is known as a sample. The sample is then used to make generalizations about the population. So for example, suppose we collect a sample of 100 students from a particular university, and we find their grade point average, and we look at the high school they attended, in an effort to determine how the high school that they attended affects their performance in college. The questions that we want to answer are, what are the who and the what of this study, and what are the population in the sample here? So the who. The who are the individuals that we sampled, the individuals on whom we're collecting information. And in this study, the 100 students are the individuals on which the data were collected. The data are the GPA and the high school. So the what? We've briefly mentioned that already. We measured the GPA and the high school the student attended. These are the what. What's the population? Well, who are we trying to make general statements about? The students at this university. So that's our population, all the students at this university. And the sample is the 100 students that we chose. We have several different types of variables. One is an identifier variable. And this is a variable for which each individual receives a unique value. And they can be useful, but not so much for analysis. So examples include student IDs and social security numbers. Categorical variables are variables that tell the group or category to which an individual belongs. So gender, political party, age group are all categorical variables. And a quantitative variable is a variable that contains numerical values with measurement units, or which have a meaningful numerical value. So speed, age, and weight are examples of quantitative variables. All right, so back to the GPA and high school example. Suppose that for a group of high school students, we measure their GPAs as well as the high school that they're attending. What are the variables in this study, and which type of variable is each one? Well, the variables, high school and GPA, those are the things that we're measuring. Grade point average. This is a quantitative variable because the value of the GPA has a meaningful numerical quantity. The high school is a categorical variable. It classifies the student based on which high school they attended. So this is a categorical variable because it's putting students into categories. Now, how do we summarize categorical data? Well, let's look at how we do it graphically and tabularly. We can do it by way of a frequency table, which is simply a listing of each category and how many times it occurs in the sample. The bar chart shows counts for each category next to each other, and the count is represented by the height of the bar. The bar chart can also be used to represent the relative frequency of each category. The relative frequency is the percentage of the time that that category occurs in the sample. So again, the relative frequency, the percentage of the time the category occurs in the sample. We can also use a pie chart, which shows the relative frequency of each category as a proportional slice of a circle. But before using any of these displays, we need to be careful and make sure that the variable that we're representing is in fact categorical. If it's not, then these displays are meaningless. So let's talk about some of these displays. So let's look at our university example. We have 14 from high school A, 16 from high school B, 20 from high school C, 20 from high school D, 13 from high school E, and 17 from high school F. And what we're going to do is we're going to make a frequency table, a bar chart, a relative frequency bar chart, a frequency bar chart, and a pie chart to describe the distribution of the high schools among our sample. So here's the frequency table. Across the top, you see all the categories, high school A, B, C, D, E, and F. We have the frequencies 14, 16, 20, 20, 13, and 17, and the corresponding relative frequencies 0.14, 0.16, 0.2, 0.2, 0.13, and 0.17. So what we see is we basically made a frequency table and a relative frequency table at the same time. Now what about the bar chart? Here's the frequency bar chart with high school 1, 2, 3, 4, 5, and 6 as the labels, 1 corresponding to A, 2 corresponding to B, 6 corresponding to F. And note that the height of each bar corresponds to the number of times that each high school appears in the sample. So the height of the first bar goes up to 14 because that's how many students came from high school A. The height of the second bar goes up to 16 because that's how many students came from high school B, and so on. We can also look at the relative frequency bar chart, which looks exactly the same as the frequency bar chart, except for if you look at the y-axis, now the relative frequencies are going down the side as opposed to the actual frequencies. Here's the pie chart of the high schools in our sample. And what we see is that each high school corresponds to a different color, and the size of the slice corresponding to each high school is representative of the relative frequency of that high school in our sample. So those are some examples of how we can summarize categorical data graphically. But there are some things that can make a chart bad. The biggest problem that we have in categorical data displays is violation of what's known as the area principle. And what the area principle says is that the area occupied by a part of the graph should correspond to the magnitude of the value it represents. So let's look at some examples of bad graphs. If we have bar charts with mismatched bar widths, then this is bad because it violates the area principle. Say high school A and high school B in our example had the same number in them. Say they each had 14 students. If the bar for high school A is wider than the bar for high school B, it's going to appear that high school A makes up more of the sample than high school B because the areas of the bars aren't the same. We don't want that. We want all of our bars to have the same width. Three-dimensional pie charts are inherently bad because when you make a pie chart, you usually divide things up by the area of the circle. But once you get into 3 dimensions, you have to worry about volume, and people don't typically account for the volume. So don't use 3-dimensional pie charts as a way to represent categorical data. Picture graphs. These are often the worst offenders of the area principle because the size of the picture, the area of the picture, is not often representative of the relative frequency of the category's appearance in the sample. So we want to stay away from those as well. We have these variables that are kind of hybrids of quantitative and categorical variables. One really common example is Likert scale data. So as an example, the question might be, how often do you exercise? And the possible responses might be 1 for never, 2 for seldom, 3 for sometimes, 4 for often, and 5 for every day. The responses do constitute categories, but the numbers have a particular order to them. And it turns out that the order of the numbers does correspond to the order of the amount of exercise. So they do have a numerical meaning. So these responses, while categorical, do also have some properties of quantitative variables, and it's important to be aware of these types of things when we look at what type of data we're analyzing. All right, so in summarizing data, there are several mistakes that we can make, and I'm going to give you a few of the common ones right here. We need to think about what question we want to answer when we decide whether to label a variable as a categorical or a quantitative variable. We need to always be skeptical. We want to be careful to think about how the data were collected, and as we move on in the course, we'll learn more about what makes a good sample and what makes a bad sample. Investigators will sometimes contrive data in such a way that it produces a desirable result. While unethical, it sometimes happens, and we need to be careful and look out for that. We need to be careful to recognize that even though a variable's values might be numbers, that doesn't necessarily mean it's a quantitative variable, because that doesn't mean that the numbers have any real meaning to them. They might just be codings. Categorical variables are often coded with numbers, but they don't necessarily have a meaning. So for example, let's say we code males as 1, females as 2. These categories would mean the same thing if they were coded 1 for female and 2 for male. So gender is a categorical variable. So we've listed the things that can go wrong. These are the things that we need to avoid when we're summarizing categorical data. We've talked about some basic terms in statistics, things that are commonly talked about, and we've talked about how to display and summarize categorical data.
All around the world, we use statistics to measure and analyze variability. People have different heights, weights, hair color, food preferences, and so on. These things are all variable because they change among different individuals. There are 2 kinds of statistics. There's inferential statistics and there's descriptive statistics. Inferential statistics deals with taking a sample and analyzing that sample to make judgments or claims about a population. Descriptive statistics refers to getting data and talking about it. So when you hear a professor say something like the average midterm score was 65%, they are using descriptive statistics. We often use things like histograms and graphs to help us summarize and explain descriptive statistics. The first part of the course deals with descriptive statistics, and the second part of the course deals with inferential statistics. In order to understand statistics, you'll first have to know some basic definitions. A population refers to the total amount of things. I say things because a population can refer to almost anything. This can refer to the total amount of people, cats, vehicles, houses, and so on. Now, a sample refers to a small part of the population that is used for study, and the total amount of things in a sample is called the sample size. In statistics, what we examine is a variable. It is what we are studying, and it can be measurable, countable, and categorized. When we talked about how people can have different heights, weights, and hair color, these are all variables. Variables represent a characteristic of what we are trying to study, and they can vary among different individuals. When we measure a variable, our data can come into 2 different forms. There is categorical data and there is quantitative data. Quantitative data refers to data that is measured in numbers. It deals with numbers that make sense to perform arithmetic calculations with, like calculating an average. Quantitative data comes from quantitative variables. Examples include height, weight, and midterm score. On the other hand, categorical data refers to values that place things into different groups or categories. Categorical data comes from categorical variables. Examples include hair color, type of cat, and letter grade. There are actually two types of categorical variables. There is categorical and ordinal, and categorical and nominal. Something is said to be categorical and ordinal if there is a logical ordering to the values of a categorical variable. A good example of this would be letter grade. We can logically order the values of this categorical variable from high to low, or from low to high. Now, something is said to be categorical and nominal if there is no logical ordering to the values of a categorical variable. An example of this would be hair color. Depending on our sample, we could have people with red hair, blonde hair, brown hair, or even blue hair. Although we can arrange these values in alphabetical order, there is no logical ordering with respect to the actual values itself. There are also two types of quantitative variables. There is discrete and continuous. Discrete variables refer to variables that can only be measured in certain numbers. An example of this is the number of pets you own. You can own 0 pets, 1 pet, 2 pets, or even 30 pets, but it's impossible for us to own 2.7 pets. In contrast, continuous variables refer to variables that can take on any numerical value. An example of this would be weight. Someone can weigh 105 pounds, 185 pounds, or even 170.683 pounds. We can measure this variable in as many decimal places as we want, which is why it is classified as a continuous variable. So to recap, a population refers to the total number of things. A sample refers to a small part of the population that we examine and extract information from. The total number of things in a sample is called a sample size. What we measure from each individual is the variable of interest. The way we measure these variables lets us know if the variable is quantitative or categorical. For example, if our variable of interest was midterm scores for statistics, we would have quantitative data if we measure each individual's test score. If instead we decide to place people into categories based on letter grade, then we would be working with categorical data. In this video, we'll be learning about the normal distribution and the 68-95-99.7 rule. When we talk about normal distributions, we refer to data we get from a population or sample. So before we actually talk about the normal distribution, we need to first distinguish the difference between a parameter and a statistic. A parameter is a number that describes the data from a population, whereas a statistic is a number that describes the data from a sample. Examples of parameters and statistics are the mean and standard deviation. But because of the definitions we just talked about, we have to be very careful with what symbols we use to represent these numbers. When we are dealing with a sample, we use the symbol x bar to represent the sample mean, and we use the letter s to represent the sample standard deviation. These are statistics. When we are dealing with a population, we use the Greek letter mu to represent the population mean, and we use the Greek letter sigma to represent the population standard deviation. These are parameters. The population parameters mu and sigma are very important when we talk about normally distributed populations. So what is a normal distribution anyways? A normal distribution is a special type of density curve that is bell-shaped. For this reason, the normal distribution is sometimes called the bell curve or the normal curve. The normal distribution describes the tendency for data to cluster around a central value. In fact, this central value is the population mean mu, which is always located in the middle of the curve. So for any normal distribution, we can say that some data points will fall below the mean, other data points will fall above the mean, but most of the data values are located near the mean. The normal distribution and its shape actually arises from many different variables found in nature, such as weight, height, volume, blood pressure, and many more. This is why the normal distribution is commonly studied. For example, exam scores are known to follow a normal distribution. Some people do great on exams, some people do poorly on exams, but a large majority of people score near the average or the mean. In this example, the average exam score is 50 because it is located in the middle of the curve. Now that you know what a normal distribution looks like, we need to talk about the population mean mu and the population standard deviation sigma. Both of these tell us important information about how the normal distribution looks. We'll talk about the population mean mu first. The population mean mu characterizes the position of the normal distribution. If you increase the mean, the curve will follow and move towards the right. And if you decrease the mean, the curve will still follow and move towards the left. This happens because the data will always cluster around the mean in normally distributed populations. As a result, the value of the mean determines the position of the normal distribution. This video, we will be looking at the mode, median, mean, range, and standard deviation. In the last video, you saw how we can display a data set using things like histograms, stem plots, and pie charts. We use these diagrams to help us visually display a data set. However, there is another way we can describe a distribution, and that way is by using numbers. The mode, median, mean, range, and standard deviation give us numerical information about the distribution of a data set. Specifically, the mode, median, and mean are measures of center or central tendency, and the range and standard deviation are measures of spread. We will look at how we can determine the measures of center first. So suppose I took a random sample of 9 people and measured their heights. Now the mode of a data set refers to the data value that is most frequently observed. Notice how the number 154 appears 3 times in this data set. This means that the mode of this data set is equal to 154. Now the median refers to the data value that is positioned in the middle of an ordered data set. Students often forget that to find the median, your data must be first put into order. We usually order the data set from smallest to largest. We can clearly see that the number 154 is in the middle of the data set because there are 4 data points above it and there are 4 data points below it. So the median of this data set is equal to 154. When a data set is extremely large, it might be helpful for us to use the formula n plus 1 divided by 2. This formula tells us the position of the median. N refers to the total number of data values in our sample. We have a total of 9 values in our sample, so n is equal to 9, and 9 plus 1 is equal to 10, and 10 divided by 2 gives us 5. As a result, the median is equal to the value in the 5th position, which is equal to 154. Note that we could have counted from the bottom and we would still get the same answer, as long as the data set is ordered. We always use the formula n plus 1 divided by 2 to find the position of the median. When we have an odd amount of data values, the median will always be apparent. However, if n is an even number, we see that we have 2 middle data points. And if we use the formula, we end up with 5.5. We see that there isn't a value in this position, so what we do is we take the arithmetic average of the 2 values beside this position. So we would have 154 plus 155 divided by 2, and we get an answer of 154.5. This value is in fact the value of the median for this data set. The last measure of central tendency we will talk about is the mean. The mean is just another name for the arithmetic average. The formula of the mean is as follows. It is equal to the summation of all data values divided by the total number of data values. If our mean comes from a sample, we call it x bar. So to get the mean for this sample, we add up all the data values, and since there is a total of 10 values, we will divide by 10. As a result, we get a mean or x bar of 165.6. Let's quickly compare between the median and the mean. Both of these are measures of center, but they measure center in a different way. The median refers to the physical middle point, so for this data set, the median would be equal to 12. Now the mean can be thought of as the balance point. If you calculate the mean for this data set, you would get a value of 10. If these people were of equal weights, this is the position in which a seesaw would be balanced. Now let's talk about the measures of spread. This includes the range and standard deviation. Both of these values measure spread in a different way. The range is simply the maximum minus the minimum, so it tells us how much room a distribution takes. In this dataset, the range is equal to the largest number, which is 196, minus the smallest number, which is 139. As a result, the range is equal to 57. Now the standard deviation is computed using this formula. The formula looks a little complicated, but the calculation for the standard deviation is simple. We will calculate the standard deviation for the following dataset. I will create a table to help me with my calculations, and this table corresponds to the numerator of the formula. Notice how x bar is contained within the formula, so we should calculate this first. You should find that the mean is equal to 15.4. The formula says we need to subtract each value from x bar, so we do this on the table. 10 minus 15.4 is negative 5.4. 12 minus 15.4 is negative 3.4. 16 minus 15.4 is 0.6, and so on. The next step is to square what we have just calculated. Negative 5.4 squared is 29.16. Negative 3.4 squared is 11.56, and so on. The next step is to find the sum of what we have just calculated. You should find that this is equal to 75.2. Remember that we used this table to calculate the numerator of the formula, so we can now replace it with 75.2. From here, the formula should be pretty straightforward. N refers to the total number of data values, and there are 5 data values in this dataset, so N is equal to 5. We can simplify this, and we end up with a standard deviation that is equal to 4.336. Now, what does the standard deviation even tell us? The standard deviation tells us how close the values in a dataset are to the mean. For example, a small standard deviation indicates a small amount of variability for a given dataset. In other words, there will be a lot of values that are closer to the mean, which makes the distribution less spread out. In contrast, a high standard deviation indicates a high amount of variability for a given dataset. In other words, there will be a lot more values that are farther from the mean, which makes the distribution more spread out. The last thing we will talk about is variance. Variance is closely related to the standard deviation. The only difference between these two formulas is that the standard deviation involves taking the square root of the calculations, and for the variance, we don't take the square root. Also, notice how for the standard deviation, we denote it as s, and for the variance, we denote it as s squared. Both of these can be referred to as the sample variance and the sample standard deviation.
In descriptive statistics, you're basically organizing and summarizing data using numbers and graphs. For instance, you could summarize your data using a bar graph, which looks like this. Many of you have seen this in middle school or high school. You could even organize your data into a histogram. A histogram looks like a bar graph, but the bars are basically attached to each other. So that's the difference between a histogram and a bar graph. You can also organize your data into a pie chart. And this is very useful if you want to break it down into categories based on percentages. Now there's other graphs too. You can organize it using a line graph. You can also use tables to organize your data. You could use a frequency table, a frequency distribution table, and there's a lot of different ways of organizing it. And so that falls under descriptive statistics. You can also describe the shape of the graph. For instance, is the data symmetrical? Or is it skewed to the right? Or is the data skewed to the left? So that all falls under descriptive statistics. Now we can also describe our data using numbers. So for instance, under measures of central tendency, we have things like the mean, the median, and the mode. Now there's 2 types of means that you want to be familiar with. The first one is the sample mean, which is basically a sum of your sample data divided by the number of data items in your sample. The second is the population mean, which is also the sum divided by the number of data items in the population. And the mean is basically the average. The median is the middle number of a data set, and the mode is basically the number that occurs most frequently. So that's another way you could describe your data, using those types of numbers. You can also describe it in terms of range, variance, and standard deviation. Now let's move on to inferential statistics. So in this branch of statistics, that's when we take our sample data and we use it to make an inference or even draw a conclusion of the population. We can even use probability to determine how confident we can be that the conclusions that we make are correct. So let's use an example to illustrate this. Let's say in city XYZ, the population is 100,000. Now, let's say we wish to make a test. How many people in this city like blue cars? How can we find the answer to this question? Now, it would be unreasonable for us to ask every citizen in this city if they like or if they prefer to purchase a blue car, because that means you have to ask 100,000 people, and that's just not practical. So instead, what we could do is take a small sample of the population, let's say 100 individuals, and ask them, hey, do you prefer to drive a blue car or do you prefer to drive a red car? And see who say yes. Now, let's say if 20 out of the 100 people in our sample says yes. So that means that 20% of people prefer blue cars. This is based on our sample. That's our sample data. So that would fall under the realm of, would you say descriptive or inferential statistics? Which one? Now, this is basically a fact. We're presenting data. So 20 people out of 100 say they like blue cars. So that would be descriptive. Now, we can use that information to draw a conclusion about the population. We can say that 20% of the entire population may be within a 2% margin of error, like blue cars. In this case, because we're making an inference or we're drawing a conclusion, that will fall under inferential statistics. Now, there's something known as confidence intervals, which also falls under inferential statistics. So we could say that we are 95% certain or 95% confident that 20% of the individuals living in city XYZ prefer to drive blue cars within a 2% margin of error. Now, we can increase our confidence and get a better picture of the population data and how they like blue cars if we increase our sample size. So let's say we increase it to 1,000 instead of 100. So if we ask 1,000 people, do they like blue cars? And let's say the data is now different. Let's say 21% says yes to it within a 1% margin of error. So this value is going to be a better reflection of the population in response to their preference for blue cars because our sample size is bigger. So now we could say that 21% of the population prefer blue cars within a 1% margin of error. So by increasing the sample size, you can make a better prediction of the population and their preference for blue cars. And so that's a basic intro between descriptive statistics and inferential statistics. So hopefully this video gave you a better understanding of these two topics.
We will be looking at the 5-number summary, box plots, and outliers. The 5-number summary gives us a way to describe a distribution using only 5 numbers. These 5 numbers include the minimum, first quartile, median, third quartile, and the maximum. So if we took a sample and measured some random quantitative variable, we could order these values from smallest to largest and use the 5-number summary to describe the distribution. The minimum is the smallest value in a dataset, and the maximum is the largest value in a dataset. The median is the middle data value. It is a point at which 50% of the data values are below the median and 50% of the data values are larger than the median. Now, the median of the bottom half is called the first quartile. It is a position where 25% of the data values are below it and 75% of the data values are larger than it. The first quartile is essentially the median of the median. The same thing can be said for the third quartile. The median of the top half gives us the third quartile, and it is a position where 75% of the data values are below it and 25% of the data values are larger than it. The 5-number summary also gives us a way to divide the data into 4 equal quarters. So let's determine the 5-number summary for the following dataset. We'll start with the median. To find the median, you can look for it visually, and you should find that the median is equal to 33. You can also use the formula to find the position of the median, and we find that it is in the 8th position, which is equal to 33. Now to find the first quartile, we can use the same formula to find the position of Q1, except this time n refers to the number of data values below the median. There are 7 data points below the median, so n is equal to 7, and we find that the first quartile is in the 4th position. So we count to the 4th position and we see that Q1 is equal to 25. To find the third quartile, we will do the same sort of thing, except n refers to the number of data values that are above the median. There will always be symmetry, so you should find that Q3 is also in position 4. So we count 4 positions above the median, and we find that Q3 is equal to 36. Now the minimum is the smallest number, and the maximum is the largest number. So as a result, this is our 5-number summary. We can then take these 5 numbers and make something called a box plot. A box plot gives us a visual representation of the 5-number summary, and it looks something like this. Each vertical line on the box plot represents a number from the 5-number summary. The horizontal line that extends out from the box are called whiskers, and the actual box itself is called the interquartile range. The interquartile range refers to the middle 50% of an ordered dataset, and it is equal to the third quartile minus the first quartile. We can also have something called a modified box plot. It's like a regular box plot, except it accounts for outliers. Sometimes outliers in a dataset aren't that obvious. However, we can mathematically check if a dataset has outliers in it. We say that a data value is considered to be an outlier if the data value is less than Q1 minus 1.5 times the IQR, or if the data value is greater than Q3 plus 1.5 times the IQR. So if you remember the following dataset, we had calculated the 5-number summary to be 10, 25, 33, 36, and 59. To check for outliers, we first need to calculate the interquartile range. We found that Q3 is equal to 36, and we found that Q1 is equal to 25. When we simplify this, we get an answer of 11. Now we said that a data value is an outlier if it is less than Q1 minus 1.5 times the IQR, or if it is greater than Q3 plus 1.5 times the IQR. At this point, we can start substituting values. Q1 is 25, Q3 is 36, and the IQR is 11. And so we say that a data value is considered to be an outlier if it is less than 8.5, or if it is greater than 52.5. If we look at our dataset, we see that no values are less than 8.5. However, we do have a value that is greater than 52.5. Therefore, we say that 59 is an outlier. And so when we make a modified box plot, we write the outlier as a dot, and the whisker will only extend to the new maximum. In this case, it is 50. So to quickly recap, a regular box plot is drawn using the 5-number summary. A modified box plot also uses the 5-number summary, but it accounts for outliers. And if there are outliers, a whisker or both whiskers will extend only to the new minimum or maximum. Similar to back-to-back stem plots, we can have side-by-side box plots. By having them side by side, we can make easy mathematical and visual comparisons between two sets of data.
So now let's switch gears a bit and talk about the null hypothesis, which is one of the foundational ideas for doing statistics. What is the null hypothesis? It is a statement. It's a statement that there is no relationship between the variables that we're trying to test for. It's important that you understand that the null hypothesis always says there is no relationship. The null allows us to assess our statistical tests and tells us whether or not to reject or fail to reject our null hypothesis. I'm a bit of a stickler for protocol and philosophy, so I say fail to reject. Some people say accept. For reasons that I won't get into here, philosophically, we never actually accept the null hypothesis. We either reject it or we fail to reject it. Remember, the null hypothesis says nothing's going on. There is no relationship between the things we're measuring. What I want to do is to be able to reject the hypothesis. If I reject the hypothesis, I know something's going on. I know I found something interesting in my test. I can write the null hypothesis mathematically like this. H sub naught is notation for the null hypothesis. The Greek letter mu is notation for a mean, an average in one group. So here I'm saying that the mean measurements in two separate groups are the same. Maybe I'm running a randomized controlled trial. Maybe I'm looking at the mean responses in my treatment group versus my placebo group. My null hypothesis says they're exactly the same. In other words, I have found no effect. Nothing is going on. I'm assuming that the thing I'm measuring has no effect whatsoever. That's my null hypothesis.
Awak tahu Sugo tak?
Mestilah tahu, tapi orang yang sudah berkahwin lebih baik jauhkan diri.
Kenapa?
Okay, thank you very much, guys, for your time, and I'll see you again tomorrow.